So here is section 4.1 for Math 110. It's a quick review of exponential functions as we move into doing some calculus with them. So if you remember from Math 22, exponential functions are in the form of a number raised to the variable x. So we're only going to deal with values of b that are both greater than 0 and not equal to 1. Greater than, not greater than or equal to. Greater than 0 and not equal to 1. So we don't want to put a negative base because then when x is an even number, we'll end up with a positive value, and when x is an odd number, we'll end up with a negative value, and that isn't going to create the exponential function that we want. So we have to use positive values. But if we use the value of a 1 for the base, then it's going to look something like this, 1 to the x, and as you use different values of, to plug in for x, you're going to have a constant function, which is 1. So that's not going to be exponential. So as long as our base is positive and not equal to 1, we should be creating things that are going to look like what we're going to graph down here in a minute. So one thing we can do with exponentials is to choose what base we want to use. So even though this problem says 4 is the base, we can change that. If we would like 2 to be the base, so we want to write this in the form of 2 to a power and figure out what constant we'd put in front of x, we can look at the number 4 as a multiple of 2. Since 4 is 2 times 2, we could rewrite the number 4 to be 2 squared. And then when the exponent is 5x divided by 2, we have 2 squared raised to that exponent. We know our properties that say if you take a base to a power and then you raise it to another power, you multiply those exponents together. So we'll have 2 times 5x over 2, which simplifies all the way down to 2 to the 5x. So these are equivalent statements. It's just that we wanted a base of 2, not 4. Here the base is 2, which is good. But what we're going to try to do first is pull these two together with a rule of exponents, which is that if you're multiplying with the same base, you can add your exponents. So this will be 2 to the 3x. And then we're going to raise all that to the 1/2 power. So now we're going to multiply, and our value for k is 3/2 in this case. Here, neither of these bases are 2, so that's what we want to deal with first. We want to call 8 2 cubed. And we want to call 16 2 to the 4th. So we're just renaming the bases to put them in terms of 2. And then we can multiply our exponents. Call that 2 to the x, because 3 times x divided by 3 is x. And another 3x, or here we're going to get 4 times 3x over 4. The 4's will divide each other out and we get 3x. And now we can pull them together by multiplying. The multiplication together by adding our exponents. X plus 3x is 4x. So in this case, k is 4. And last but not least, we can rewrite this as 10 over 5 raised to the x, because if they both have that same exponent, there's a property that says you could just put the exponent on the quotient. Instead of doing the quotient of the exponentials, we can do one exponential with a quotient on the base, and that means 2 to the x, which means k is 1. To graph them, if you remember in Math 22, when you graphed them, the exponential function went through this point 0, 1, as long as we didn't have any addition or subtraction going on, because when you plug 0 in to the function 2 to the x, you get 1 out. So this was a point on our exponential, and then if we plugged 1 in, we get 2 out. If we plug 2 in, we get 4 out. So what happened on the right was larger values of x made our exponential increase like that. And if we went the other way with -1 and -2, we ended up getting smaller values like 1/2 and 1/4. But what happened on the left is the values just got closer and closer and closer to 0. And draw that very nicely. But they never get to 0, because there's never a power you can put on the number 2 and get the answer of 0, or any negative answers either. So this axis here is a horizontal asymptote. And we come closer and closer and closer, but what we realize is that 2 to the x always gives out positive values. So then you would talk in Math 22 also about, well, what happens when you put a negative inside the function? And the result of putting a negative inside the function is you flip on the y-axis, which means that it's still true that if you put 0 in, you get 0 out, because there is no -0. Putting 0 in is always going to give you 1 out. But everything else is going to do the exact opposite of what it did over here. Because when you put 1 in, you're going to get 1/2 out. When you put -1 in, you're going to get 2 out. So exactly what was happening over here on the right is going to happen to the left, and vice versa. We're flipping across the y-axis. Either way, this function is either always increasing, or if you flip it over, it's always decreasing. And so since functions are always increasing or decreasing, we know that they never take on the same y value twice. So as it increases, it just keeps on taking bigger and bigger and bigger and bigger y values, but it doesn't ever turn around to take those y values again. And that's going to help us as we go to solve equations. And so one thing we know about exponential equations is if the bases are the same and you're setting them equal, that's going to have the effect of setting the exponents equal. And there will be one particular value of x that will allow the left and the right-hand sides to be equal, and that's 3/5. If you have a situation where you don't have an exponential on both sides, then you want to isolate the one exponential that you have here, the base 2.7, and your x is in the exponent. This is exponential. But you want to get rid of this 4 because it's not an isolated exponential right now. So if I want it to be isolated, I'm going to divide both sides by 4 and get something that looks like this. And now that my exponential is isolated, I can see that I actually do have the same base, 2.7. 2.7 on the left to the 2x minus 1 equals 2.7 to the right to the first. And I can use the same idea here and set my exponents equal and solve and realize the value of 1 will make the left-hand side equal to the right-hand side. So I always want to check. So what I'm saying is that 4 times 2.7 raised to the 2 times 1 minus 1 power equals 10.8. So that works. That checks out. If we're looking here at C, we want to do sort of what we did up here with the bases. We'd like to have the same bases on both sides so that we can then compare the exponents. So 2 to the 3x, I can change the number 4 into 2 squared, and then I can combine these together. So 2 to the 3x should equal 2 to the, add these exponents together when you're multiplying with the same base, And now that I have the same base, I can set 3x equal to 2 plus 5x and solve that and figure out that x should be -1. When x is -1, then the left-hand side and the right-hand side will be equal. For D, I got the same idea. I've got a 2 to the -x here and a 2 to the -x here. So what I could do is factor that 2 to the -x out, because there's one here and there's one here, and what's left in the subtraction, what'll be left on the left side of the subtraction is a 1 plus x minus, on the right hand side, that 5. And remember we said that this 2 to the x or 2 to the -x never take on the value 0. So I can say for certain this is never equal to 0. But this might be. And since they're multiplied together, I want to know is there a value of x that will make this piece 0. So I want to know whether 1 plus x minus 5 could equal 0, which means can x minus 4 equal 0, which is, yeah, if you pick x equals 4, then this piece will be 0. This piece will be 1/16, but they'll multiply to 0. So that's my solution. A couple more problems to try. Looking at E, I tend to like, there's lots of different ways to do this problem, but what I tend to like to do is put everything in terms of a base 2. So that would mean the only thing that I need to change is 8. I'd like to call that 2 to the 3rd power. And then I could simplify this part. Well, actually, I think I'll go a different way. I'm going to move this whole thing over to the other side. And the reason I'm going to do that is I like to have 2 to a power equal 2 to another power, so I can set the exponents equal. So if I have it on the other side, that'll be a little easier than trying to figure out how they subtract to 0. But if they subtract to 0, that means they were equal to each other. So I have 2 to the x equals 2 to the 3 minus 2x, because when I divide, I subtract my exponents. So now again, I'm in a place where I can set that exponent equal to that exponent because the bases are equal. So when I solve that, I'll get 3x equals 3, x equals 1. So that means 2 to the 1st minus 8 over 2 squared is 0. You can check that on your calculator if you'd like. For F, I gave a little hint. We've got this thing that's called 2 to the x right here. And we've got something here that's like it, but the exponent's different. So the hint is, let's use this other variable and try to express this, let's see, we'll write down everything we got here. So 17 times the thing I'm calling x plus 4 equals 0, and try to express this in terms of capital X. So what you might notice is that this is like 2 to the 2nd times 2 to the x plus 1. Because if you were changing it into a multiplication problem, sorry,